consider an object being heated or cooled down. As heat propagates through the object, it slowly takes the structure of the medium it is flowing through. This leads us to a compelling question. Can we infer an object's shape by observing its heat flow? In this work, we leverage the physics of heat conduction to reconstruct an object's shape from its thermal video. The video is captured only by illuminating the object using ordinary incandescent lamps, which sufficiently induces heat conduction for shape recovery. We recover the object's shape in two steps. First, by inverting the heat equation to obtain a shape-dependent Laplace-Beltrami operator, and then performing a second optimization to recover the object's shape. Heat transfer occurs in a medium due to three fundamental phenomena, namely the conduction, convection, and radiation. A continuous heat equation that takes into account all three different modes of heat transfer can be written as shown. Here, the term delta is a Laplace-Beltrami operator that encodes geometric information about an object. This Laplace operator, in its discrete form, can be approximated through a mass matrix and a Laplacian. Treating the elements of the Laplace operator as unknowns, we can write a discretized heat equation that is linear with temperature and independent of objects embedding in space. Solving this linearized heat equation with temperature measurements from a thermal camera, we obtain properties such as heat capacity of the object, convection coefficient of the surrounding medium, the absorbed heat flux, and the Laplace operator that encodes geometric information. Recovering shape from the estimated Laplace operator is not a trivial problem. This is challenging as the optimization is non-convex and heavily influenced by the initial estimates. The recovered shapes from spherically convex and concave initializations show the non-convexity nature of this objective. Further, solving the objective does not guarantee the desired outputs because of inherent ambiguities in shape estimation. And moreover, our estimates of Laplacian come from noisy temperature measurements. In our approach, we constrain the optimization to have deformations only along the camera ray. This restricts the space of possible isometric deformations along the ray direction and to only occur within the silhouette of the object. Further, we resolve the remaining shape ambiguities with videos from two uncalibrated light sources and leverage the knowledge of their absorbed heat flux to introduce a normal constraint in our optimization. Incorporating the normal and camera constraints recover sufficient high-frequency details. However, with temperature measurements being noisy and Laplacians acting as high-pass filters, this hinders the faithful reconstruction of low-frequency features. To address this, we employ a coarse-to-fine refinement strategy by performing reconstructions using a coarser mesh and using them as initializations at finer resolutions. Now, we present shape reconstruction results alongside the thermal videos used as inputs. Each video is recorded with light sources positioned on one side of the camera. To highlight ample heat absorption and conduction, the respective videos have been normalized based on the maximum temperature within each. Additionally, It is important to acknowledge that our optimizations are initialized with flat planes. We present a new method for shape recovery using heat conduction, adding to computer vision's shape from X techniques. Notably, we are the first ones in computing the intrinsic shape properties from thermal videos, which has broad applications in structural analysis, computer aided design, and material science.